Hello everyone, my name is Aleksander Kubica and today I would like to tell you about single-shot error correction and universal computation with the subsystem toric code. This is a joint work with Mike Vasmer and Joe Iverson. Our community would like to build a quantum computer. This is a difficult task, and one approach which is realistic and resource efficient to building scalable quantum computers is based on topological quantum codes. And what I mean in this context by realistic is an approach which can be realized in 3 spatial dimensions with geometrical local quantum operations. The archetypal example of a topological code most of you must have heard of is the toric code, which can be realized with a planar architecture and geometrical local parity checks. So now let's see what happens if there are some measurement errors happening. In that case, we cannot trust measurement outcomes, but we can still perform reliable quantum error correction with the toric code. Namely, it suffices to repeat parity check measurements. However, there's a problem with this simple approach. If we keep repeating measurements, this leads to a significant time overhead. And this time overhead is a bottleneck to quantum computation. Ideally, we would like to cut down the time overhead. Recently, there have been quite a few ingenious ideas how one can avoid repeating measurements. However, if we apply them to the 2D toric code, we will lose geometrical locality of the model. So what we propose in our work is a different solution. We provide a realization of the toric code, which is capable of single-shot quantum error correction, which was introduced a few years ago by Bombin. So in this context, what I mean by single-shot quantum error correction is a way to perform reliable quantum error correction with geometrically local quantum operations without performing multiple rounds of measurements. In the talk, I will be talking about single-shot quantum error correction in 3 spatial dimensions, and this should be contrasted with self-correction, which we can achieve with the toric code. However, this requires 4 spatial dimensions. So let me spell it out. The main result of our work is as follows. We introduce a new quantum code, the 3D subsystem toric code, and we show how one can perform single-shot quantum error correction with it. Also, we describe how to perform fault-tolerant universal gates. So here's the outline of the talk. I will start by introducing the model. Then I will tell you how to perform a single-shot minimum perfect matching decoder in the model. And then I will say a few words about how to prove the single-shot quantum error correction property of that model. And lastly, I will briefly discuss how one can perform fault-tolerant universal gates in that model. So let's get started. Subsystem codes can be viewed as a generalization of stabilizer codes. And there are a few reasons why one can consider subsystem codes over stabilizer codes. First, subsystem codes might have smaller generators, which we need to measure. Also, subsystem codes might allow us to avoid certain no-go results. For instance, the Easting-Knil no-go theorem. However, there's a drawback because the operators we measure don't necessarily commute with each other, and thus their measurement outcomes might be random. So now let me introduce the 3D subsystem toric code. This model is based on the cubic lattice. One particular instantiation of the subsystem toric code is based on the cubic lattice. And notice that the cubic lattice, in the cubic lattice, I can color its volumes in red and blue in an alternating fashion, and 2 neighboring volumes sharing a face will be colored in different colors. I will place qubits on the edges of the lattice. And then in the bulk, for every red volume, I will introduce X-type gate generators. And for every blue volume, I will introduce Z-type gate generators. For every volume, I introduce 8 gate generators, and each gate generator is of weight 3. And on the boundary, I introduce some other operators. On the side boundaries, and there is a bunch of weight 2 operators. On the top and bottom boundaries, and there are weight 4 operators. And the stabilizer generators of that model are identified with the qubits, and they are of weight 12. If the linear size of the cubic lattice, of the region of the cubic lattice where I define the model, is L, and then the parameters of the code are, roughly speaking, and the number of physical qubits is roughly speaking 3L cubed. And then there's one logical qubit, and the distance is L plus 1. And the logical operators of the code come in 2 flavors: Baire operators and rest operators. Baire operators commute with all gate generators, and they form 2-dimensional sheet-like operator. And the rest operators form 1-dimensional string-like operators. Importantly, logical operators can be fully supported on the boundaries of the system. As we just discussed, in the bulk, the gate generators are of weight 3, and this is important because the smaller the operators are, the easier they are to realize. And also, if they are of weight at most 3, then there are no Hooke errors in noisy measurement circuits. However, in the top and bottom boundaries, they have some gate generators of weight 4. But if we look closely at those boundaries, we can see the 2D stabilizer toric code there. And in that context, the problem of reducing the weight of operators was solved. So we can use a similar solution to in our setting, and we can reduce the weight of gate generators. And how do we do that? Well, first we introduce unentangled ancilla qubits depicted here by gray dots, and then we implement a constant depth circuit composed of C0 gates. For the resulting code, we can find gate generators as depicted in the figure, and all of them are of weight at most 3. Here, I would like to make a remark that there have been previous works in which a subsystem version of the 2-dimensional toric code was considered. However, those previous models were not truly subsystem version of the toric code in the following sense. One could implement a constant depth circuit and remove those non-commuting terms from the model. And this would result with a code which is nothing but the 2D stabilizer toric code. And I would like to contrast that with our work, which is the first genuine subsystem version of the toric code. So far, I showed you one particular realization of the subsystem toric code on the cubic lattice. Our construction is more general. It can be defined on any lattice, in fact. So let me switch the picture and talk about the model in the so-called dual lattice picture. So the 3D subsystem toric code can be defined on a lattice, on any lattice, which comprises octahedral volumes, and we require that the vertices of that lattice are colored in red, blue, green, and yellow in the following way. For every octahedron, 2 of its antipodal vertices are covered in red, 2 of its antipodal vertices are colored in blue, and 2 of its antipodal vertices are colored in green and yellow. An example of such a lattice is depicted here on the slide. We place qubits on octahedral volumes. And now gate generators are associated with the edges of that lattice. And what it means is that for every edge, the corresponding operator is supported on all qubits around that edge. In particular, we have X-type gate generators on edges connecting red-green vertices and red-yellow vertices. And we have Z-type gate generators on edges connecting blue-green and blue-yellow vertices. Stabilizer operators will be associated with the vertices of that model. In order to have some logical qubits encoded in that code, we need to consider lattices with the boundary. And those lattices can be obtained in a simple way. We start with lattices without the boundary, and then we remove some octahedral volumes from those lattices. Also, our reconstruction is a generalization of the stabilizer toric code in the following sense. We can fix the state of gauge qubits of the subsystem toric code, and in that way, we will recover the stabilizer toric code. Our construction works in higher dimensions too, and in higher dimensions, we will obtain the subsystem version of the higher dimensional toric code. Also, as a remark, our construction is reminiscent of the gauge color code construction. And now let me shift gears a bit and talk about the structure of measurement outcomes. In order to diagnose X errors, we measure Z gate generators. To diagnose and correct Z errors, we would measure X gate generators. But the process is the same. So from now on, I will focus only on X errors. So the Z gate generators we measure are not independent. And namely, if I multiply gate generators around every cube, then I get the identity operator. Similarly, if I multiply gate generators around each vertex, I get the identity operator. So what it means is that the corresponding measurement outcomes have to satisfy certain local consistency checks. What I refer to on this slide as the gauge flags is basically the set of all measurement outcomes which return -1 outcome. So if we want to talk about decoding, it is necessary to switch to the dual lattice picture. So in the dual lattice picture, I will have blue, green, and yellow vertices, and those vertices can be thought of as the locations of local consistency checks between the measurement outcomes. I will also have green and yellow edges. Those are the edges which correspond to Z gate generators. They connect blue, green, and blue, yellow vertices. And I can also add gray edges which connect blue vertices. They will be the edges where qubits are placed. And now in this dual lattice picture, I can express those local consistency checks as the following so-called Gauss law. And it can be visualized quite neatly. And this Gauss law says that the gauge flags forms loops. So if I observe some gauge flags, it has to form closed loops. It is not a collection of chopped strings. Okay, so I depicted a possible configuration of the gauge flags. So now let me depict also a possible X error. So if I have some X error in the system, and then this error would result in the stabilizer syndrome, which is depicted in this figure as blue dots. However, the stabilizer syndrome can be found differently. And the stabilizer syndrome can be found as the locations where the gauge flux changes color. And this is an important observation which is used in our decoding, which I'm about to describe. So if we have measurement errors, then the observed gauge flux will violate the Gauss law. So instead of seeing a collection of closed loops, we will see a bunch of strings. So now we're ready to describe the two-step single-shot decoding strategy. In the first step, we can identify the locations where the Gauss law is violated, and we can close the broken gauge flux loops. And then, having a collection of loops, we can estimate the stabilizer syndrome by finding the locations where the gauge flux changes the color. Those locations are depicted by blue dots. And in the second step of this decoding strategy, we can find an appropriate recovery operator by basically pairing up the locations where the blue dots. Importantly, both steps of this decoding strategy reduce to pairing out vertices within the dual lattice picture. In our decoding, we use the minimum weight perfect matching algorithm. And this is important because the minimum weight perfect matching algorithm leads to a good performance, but it is also needed in our proof of single-shot quantum error correction. Also, I would like to highlight that it is likely that there is some non-trivial residual error left in the system after we perform one round of single-shot quantum error correction. And this is because we don't know the syndrome exactly. So we did some numerics. We considered the case of the IID Pauli X errors and measurement errors, and they are both of the same strength. And what we study is how errors accumulate during repeated rounds of quantum error correction. And within each round of quantum error correction, what we do is we add new errors to the pre-existing residual noise. Then we extract gauge measurement outcomes, and those measurements can be faulty. And then we perform a single-shot minimum weight perfect matching decoder, which I just described, using only the information from that round of error correction. And we repeat that multiple times. So for instance, in the plot, I show the logical failure rate as a function of the error strength after 4 rounds of quantum error correction for different code distances. So what we can study now is the so-called storage threshold. I can consider the limit of taking many rounds of quantum error correction. And what we observe is a threshold of above 1% for that model. And remember, here I have both Pauli X errors and measurement errors. Also, I would like to add that we expect the performance for the circuit level noise should be similar because the operators we measure are of small weight. Okay, so now let me tell you a few things about proving that the model has a single-shot quantum error correction property. So just to recap, single-shot quantum error correction tells us that one round of local parity check measurement suffices to perform reliable quantum error correction, even in the presence of measurement errors. So what we need in order to establish that property, we need an assumption about the errors. So basically, we say that errors are p-bounded if and only if for any subset of locations A, the probability of errors affecting that particular subset of location and possibly other location too, that probability is exponentially suppressed in the size of A. And an example of a p-bounded errors would be, for instance, the IID errors with rate p. However, we can have some correlations among errors. They have to be suppressed though. So to formulate our theorem, we need a few notions. So first, let me introduce a class of recovery operations denoted by R subscript eta. Those recovery operations consist of single shot minimum perfect matching decoder with eta bounded measurement errors. Also, another class of channels which we need to define is the noise n subscript tau epsilon. And this class of channels comprises Pauli X errors such that they are equivalent to some t-bounded errors, and their logical failure rate when we apply the noiseless minimum perfect matching decoder to them is at most epsilon. Okay, so equipped with those two notions, the recovery operations and noise channel, we can state our theorem. So the theorem says that for sufficiently small eta and tau, those are the parameters which describe the measurement errors and the Pauli errors. For sufficiently small eta and tau, there exists tau prime and epsilon prime, such that the following inclusion holds. So tau prime and epsilon prime describe the residual noise left in the system. In other words, what our theorem says is if we have some initial noise in the system, and if we apply some recovery to it, then the resulting residual noise will be of the same type as the initial noise. The parameters of the residual noise will be slightly different than the parameters of the initial noise. And how do they change? Well, let's see that in the next slide. So this is the statement of the theorem. And here I just want to mention to you that there are very many constants which I'm sweeping under the rug. They depend on the lattice details, but they're not that important. But what is important is that the residual noise is suppressed if measurement errors are suppressed. So this is captured by the following. The limit of tau prime as eta goes to 0 is 0. And the other important feature is that the increase in logical failure rate vanishes as system size increases. And this is captured by saying that the limit of epsilon prime as L goes to infinity, L was the linear system size, that limit is epsilon. Okay, so now we can, using this theorem, we can say what happens after n rounds of single shot quantum error correction. Then we have the following inclusion, which basically says that, that after those n rounds, the residual noise stays tau prime bounded, and the logical failure rate grows slowly, grows linearly in n. And so what this means is that the residual noise does not accumulate in an uncontrollable way, and as a result, the encoded information is well protected for a long time. So now in the few last minutes, let me say a few words about fault-tolerant universal computation and the gates which can be done in this model. So in order to carry out computation, we need a universal set of gates. And such a gate set consists, for instance, of the Hadamard, the T, and the C-not gate. Logical gates, which can be implemented via transversal gates, are nice because they're easy to implement, and they're a tensor product of single qubit unitaries, or maybe unitaries which act on a few qubits, if we consider partitions of qubits which are not single qubit partitions. And those transversal gates are trivially fault tolerant, because if one qubit is affected by some error, if we apply a transversal gate, this error does not spread. However, there's a limitation. There's a theorem by Easting-Kneel which says that for any non-trivial quantum error correcting code, the set of transversal gates is not universal. And there's a way, however, to circumvent the Easting-Kneel theorem, and this is possible if we use subsystem codes. So basically, what we propose is to switch between two codes with two different sets of transversal gates, and those two sets combined allow us to have a universal set of gates. So in particular, the logical Hadamard and CNOT gates can be realized in the 3D subsystem toric code, and the missing gate, the logical T gate, can be realized in the 3D stabilizer toric code. Also, let me emphasize that code switching can be realized fault tolerantly via gauge fixing in constant time. So just to recap, what we describe is a way to perform fault tolerant universal computation without magic state distillation and with no time overhead in constant time. So how do we do that? We consider the 3D tetrahedral code based on the 3D subsystem toric code. So what is it? So instead of taking the cubic region of the cubic lattice, we consider a tetrahedral region within the cubic lattice. And in that region, we have 3 copies of the toric code, which are fused along the base. So as depicted here, in the top of the model, at each location, I will have 3 qubits. In the base of the model, I will have just 1 qubit at each location. And this construction is related to the idea of local unitary mapping between the color and toric codes. And there is a talk by Mike Vasmer and myself where we explain, where we flash out this idea too. So what are the gates we can straightforwardly implement in this model? Those gates include the CNOT, the logical CNOT gate, which is implemented transversally, the logical CZ gate, which is implemented as a physical CZ gate between certain boundaries of this model. And also we can implement the logical Hadamard gate by applying the Hadamard gate to all the qubits in the base, and the swap gate to the qubits in the top of that tetrahedral code. So how do we do the T gate? The logical T gate can be done first by gauge fixing the subsystem toric code to the stabilizer toric code, and then implementing the T gate to all qubits in the base, and the CCZ gate to every triple of qubits in the top. Also, let me remark that if we only have access to planar architectures, our ideas can still be realized, but then we need to consider the 2+1D measurement-based protocol with just-in-time decoding, which was introduced by Bombin a few years ago. Okay, this brings me to the end of my talk. So in the talk, what I presented to you is a new topological quantum code. the 3D subsystem toric code, which is very interesting. I showed to you how one can perform a single-shot quantum error correction with that model by using the single-shot minimum weight perfect matching decoder. Also, I told you a bit about what it means to prove that this model has single-shot quantum error correction property. Lastly, we discussed how to implement fault-tolerant universal gates in that model, and those gates are implemented in a fault-tolerant way. We don't use magic state distillation. And with that, I would like to thank you for your attention. If you want to read more, please check our paper on the archive. Thanks a lot. Bye.